All right, so in order for us to begin with our actual work and our actual learning, we are going to introduce a simple learning task, okay, classification task, which will be our running example for the day, also known as our case study, okay? We're going to use a multi-layer perceptron that you learned about yesterday, and we are going to have a specific data set. We're going to start from a simple version of the MLP, which will make more complicated, so we can along the way learn about the various reasons why we do all of those optimization tricks that we do, okay? And once at the end of this section we have introduced all of those elements that we need, then we're ready to start doing optimization, okay? So let's lay down the foundation, as we say, and let's start with our data set. This might be the most celebrated, or one of the most celebrated data sets in machine learning, okay? And the credit goes to Yann LeCun in 1998, okay? And it's called MNIST. It's the Modified National Institute of Standards and Technology Database, okay? So for short, MNIST. And on the right of your screen, you are looking at some examples from this data set, okay? So it's a bunch of digits. Digits from 0 to 9, right? 10 digits. And they're taken from actual handwritten envelopes, I believe, scanned and categorized like this. So different people write the same digit a different way. So one of the first applications that were deemed to be interesting are the automatic classification of handwritten digits. Because that can be super useful, for example, for the USPS or the postal services of any country, really, that would like to rely on a zip code or something like that that is numerical for routing and automatically sorting mail, okay? So this is MNIST, and it's a great simple data set for us to build on, okay? How does it look like? When we zoom into the data set, we're going to see two sets of examples, okay? We have 60,000 training images, we have 10,000 testing images. The typical processes we will focus our training efforts to learn a model and validate it also on that first 60,000. And then we are going to touch the 10K test set only at the end to evaluate how well we have done, okay? So each example is a pair of X and Y. X is the image, okay? And Y is the label. Now the image is a 28 by 28 pixel image, right? So we can look at it here in the picture on the right. It looks like a big array, two-dimensional array, or like a matrix, where each cell of this array has a certain intensity, light intensity, right? So there are some squares that are dark, some squares that are bright, etc. And that is the grayscale value of the pixel, and it's it's graded between 0 and 255. These are integers. Okay, so 1 byte essentially for this information. Now the label accompanying the image is a number from 0 to 9, which is tells us what is the true digit that this squiggle is supposed to represent. So this is what our data set looks like. Now, for some of the notions that we introduce and some of the ideas we discuss, we need a mathematical model for our data. Okay, so the most overwhelmingly the most common assumption we make about our data is that it is all examples are drawn independently and identically distributed, IID, from the same data distribution, okay? And that's the second bullet here. And we will draw n examples, n equals 60K in this case, for our training set, which we will signify by S, okay? That's the notation we use. So what is the model we will use? We will use a multi-layer perceptron, okay, an MLP, which you learned about yesterday. And in this particular example that you will see on the right of your screen, and by the way, some of those visualizations were taken for machine learning for artists, which is a great resource, a great online free collective resource of visualizations for machine learning. Some of them more practical, like this one. Some of them of high aesthetic value, let's say, more artistic value. I encourage you to study this kind of resource. There's a lot of interesting things in there. Okay, so this is one particular example of what we're trying to achieve, right? On this visualization, we have on the left, we have an image coming in that looks maybe like a 7 or maybe also kind of like a 1, and somehow we will give it to our multi-layer perceptron. In this particular case, we have one hidden layer, okay? And in the output, we're expecting to get something that looks like confidence, something that looks like typically like a probability mass function, okay? Because we're going to use a softmax in the output. Actually, in the end, the outputs, we can interpret them as probabilities. So our network will tell us, our model will tell us, I think this is most likely a 7 because I will give you a high value on the output 7, right? Or maybe it is a 1, but that's less likely, okay? And it's highly unlikely that it is a 0 or a 6, okay? This is one example. And if we change the example and we replace it with a 4 that we see here in the input, then it should give us a high value on the 4, right? So you've seen some of these concepts. This is what we're trying to achieve, but we have a little problem here that we need to cover. This MLP, the multi-layer perceptron, takes as an input a long vector, right? This is a long vector of values. But our images are represented as, let's say, matrices, as a grid, 28 by 28. What are our options here, right? I should give you a forward reference that you should look forward to week 2 and day 1, okay, where you're going to see the right way to do this using convolutional neural networks to use the full spatial information in your images. But our simple approach for now is we are going to take these 28 by 28 values, we're going to stack them in one long vector, okay? That is the simple approach we're going to use for now. Okay, and this is how it looks like, okay? From the same source, we have something that looks like a 2, maybe on the left, okay? 784 pixels, and they can be represented as a matrix in the middle where we see the actual intensity values as integers, and then we stack them in a long vector from pixel 1 to pixel 784, and that's it. It goes into our model. Okay, this is how we're going to handle things in practice for today. Okay, so what is our model? Okay, we're going to use our multi-layer perceptron to make a prediction. We're going to give it an input x, and it's xi for the ith, let's say, example that we have, and it's going to make a prediction y hat of I. That's a predicted label. And our model is parameterized by the weights w. We're kind of hiding the biases inside the weights also. So we are assuming that there's one vector w for today that includes all the weights and all the biases stacked in one long vector also. Okay, so how does our MLP look like? It has the structure that you see at the bottom. We're composing layer by layer the sequence of the following transformations. We have an affine transformation. We take the input x, okay, input, we do a matrix vector multiply, plus we add this constant vector, right? I'm sorry, we add this constant vector. This is an affine transformation. And then we apply this non-linearity, sigma, okay? And then we continue. The output of sigma is our hidden layer, okay, our first hidden layer here, and that becomes the input of the next layer. Affine transformation, non-linearity, and so on and so forth, until we go to the output of the last layer, where we apply a different non-linearity. We apply the softmax that you saw yesterday, and its goal is to turn those outputs of the last layer into probabilities. Okay, so at the end of the day, all of those outputs are going to sum to 1. They're going to be non-negative, and this is due to the softmax. So this is the model we're going to use. It should be familiar. So let's see what else we have. Part of one little thing that you will see in your lab is this visualization exercise. So I will try to explain the basics, but you will see more on your notebooks. So how do we visualize MLP parameters? It can be helpful for debugging, etc. So imagine we have a one hidden layer network, right? Input, hidden layer, output. And we choose arbitrarily that we will have 10 hidden units. So what we see here on the right is an example of that, okay? We can consider each one of the 10 hidden units, and by the way, 10 here is arbitrary, it doesn't have to match the number of classes, it's a coincidence. So for each one of those hidden units, we can actually see how much each input contributes to the particular hidden unit, okay? So let's say hidden unit 1, if a particular input leads into this first hidden unit with a high positive value, we see a bright pixel here. If it leads to that first hidden unit with a small value, we see a dark pixel here. So we can see essentially some of the patterns that were learned during this process, okay? And you will see that much better in the notebook. And we call these filters, okay? So now, what happens in the last layer, the output of filter 1 contributes to the class 0 with a positive weight. It contributes to the class 4 with a negative weight, etc. So if you look at these bars and consider them as the weights leading from the hidden layer to the output layer, that you can get for each output, let's say output 1, you can get a weighted sum of all of these filters, which will give you a prediction for the class 1, which you will feed into the softmax along with all of the other predictions for the other classes. Okay, so more on this on your lab right after we finish this section. So what are the losses that we use? Okay, the other element we will need here are those losses, which are very important for us to be able to train our models and achieve ideally the right outcome in the end, okay? So, like we said, each example is a pair of input X and output Y, okay? And we use our parametric model, FW, to make a prediction for input Xi, which is called Y hat I. Now, how do we know whether we're doing a good job? Remember, you saw a number of losses so far. And what is a loss is a function that takes as an input two labels. Typically, we give it the true label and the predicted label. Okay? And then this loss will tell us how badly we are doing. If it's a high value, we're doing terribly. If it's a low value, we're doing well. And you have seen so far the mean square error on day 2. You have seen the cross entropy loss on day 3. And I should also mention the 0-1 loss, which gives us accuracy. Okay? The 0-1 loss takes the value 1 if we're predicting incorrectly, takes the value 0 if we're predicting correctly in classification in particular. Okay? All right. So what is our goal? Since we're discussing objectives and choosing the right objective, etc. Our ultimate goal is to learn a model that generalizes well, okay? At least on the level on this mathematical level, because we will discuss later the higher societal level also, okay? So we want to learn a model that generalizes well. So assume that we have fixed our favorite loss L, okay? Someone told us this is the loss, or we decided that this is the loss. Then we need, ideally, to minimize risk. And what is risk? It's this quantity that you see on your screen. It's the expected loss of our model on unseen data. Remember, we make this assumption that all data points x, y are coming drawn IID from the same distribution D, okay? So given that there's a distribution on our data points, we can take an expectation of the loss for unseen points, x, y. Are we making a good prediction, right? So ideally we want this risk to be small, and if we had our way, we would be minimizing this risk. Unfortunately, we do not have access to the data distribution. We only have access to a sample that we drew from the data distribution. So we have to adopt a surrogate objective. Instead of that expectation that we had in the previous slide, which is not possible to calculate because we do not know the actual data distribution, we have this empirical surrogate, okay? It's called the empirical risk. It has a little hat on top of its head, and it is this average. From 1 to n training points, we average the losses on all of the training points that we achieve with our model parameterized by W. Okay? This empirical risk tells us how well we're doing or how badly we're doing actually on the training set. And it's unfortunately not always 100% representative of our performance on unseen data, the actual risk, which is our goal. However, when n, the size of the training set, is large enough, it is a pretty good approximation. It's sufficiently good approximation, and that's what we use in practice. Okay, so this becomes our surrogate goal. Inevitably, as we discussed, we go from wanting to minimize risk, we accept that we cannot minimize risk, and we set as our secondary goal to minimize the empirical risk. Okay. So for today, this is our running example. We're doing classification on MNIST, okay? We will start with a simple linear model. So for the very first step, there will be no hidden layer. We will add it later, so you can see how the complexity of things changes. And we want to learn the parameters W by minimizing the empirical risk, okay? How do we start with that? What is our first method? It's coming up after, okay? And as a summary, these are the 5 little sections that are structured in the following way. On the left column, we have challenges, common challenges when doing optimization for machine learning. On the right column, we have the solutions. So we will see that random search is problematic, and we will see how gradient descent poses a good solution. We will see a notion called poor conditioning that causes us significant slowdowns, and how methods like momentum can help. We will see how non-convexity can be a headache, and how over-parameterization can help. We will see what that means. We will discuss how full gradients are super expensive to compute, okay, and how stochastic gradient descent and mini batches are a great solution. And finally, we will discuss the need for hyperparameter tuning and how this is actually quite costly, and how adaptive methods might be a very good solution to this challenge. So that's the end of this section. See you at the next one.